All right, so we've been talking about how to tell whether a series converges, and there's like a whole zoo of convergence tests. The comparison test, the integral test, all these different things that you can use to try to determine whether a series converges. And at the risk of saying something super controversial to other mathematicians, I feel like there's one that's kind of the best, or it's at least my favorite, and it gets the job done in many useful cases, and that's the ratio test. So that's the one that we're going to focus on. And here's how the ratio test works. If you have a series, so sum of an out to infinity, then you take the limit as n goes to infinity of the absolute value of the ratio of the n plus first term to the nth term. And if that limit turns out to be less than 1, the series converges. If it's greater than 1, the series diverges, and if it equals 1, the test is inconclusive. And again, just if you're still getting kind of used to what this is all about, this test does not tell you what the series converges to. It will just tell you, if L is less than 1, that it in fact converges. Okay? So here's an example. Say we have the sum of this complicated looking series. It's n squared over 2 to the n. So I wrote out the first few terms here, and they follow a not super easy pattern. So, what's the sum? Who knows? I can't see it, obviously, or even see if it exists. So what I'm going to do is do the ratio test. I take the limit as n goes to infinity of the absolute value of a bunch of stuff, and the first thing is a n plus 1. So I take this formula, and everywhere there's an n, I substitute an n plus 1. So that's n plus 1 squared over 2 to the n plus 1. Excuse me. Then I have to divide by the nth term, a sub n, or another way I can do that is by multiplying by the reciprocal of a sub n. So I'm going to multiply by the reciprocal of this. That's 2 to the n over n squared. Then I'm going to just do a little bit of kind of house cleaning. That's the limit as n goes to infinity. I'm going to put these kind of polynomial-like terms together. That's n plus 1 over n quantity squared. And then 2 to the n over 2 to the n plus 1 is just a half. And then we can look at the limit. We can look at what happens as n gets big to this part that involves the n's. And when n's huge, adding a 1 doesn't really do anything, doesn't do very much. So it's like you have n squared over n squared. Well, that's 1. So the limit as n goes to infinity of this whole expression is the absolute value of 1 times a half, which is a half. That's our number L here. Since a half is less than 1, we conclude that the series converges. All right, here's another example, just quickly. We can take the harmonic series, that's sum of 1 over n, 1 plus a half plus a third, and so on. We can try to apply the ratio test, so that's the limit as n goes to infinity of the absolute value of a n plus 1, which is 1 divided by n plus 1, and then we have to divide by a n, and that's multiplying by n. So the limit as n goes to infinity of n over n plus 1, absolute value, equals 1. This is a case where the ratio test is inconclusive. So we don't know from performing this test whether this particular series converges or diverges. It is helpful for me to tell you that the harmonic series diverges, so you can kind of put that in the back of your head, but this particular test doesn't tell you. Okay, thanks for listening.